Hello. In this video we will be looking at a very important aspect of polymers called as the glass transition temperature. So, how a melting point temperature is important for metals, this temperature or the glass transition temperature that is that important in terms of polymers. So, in this video we will see how do we define this glass transition temperature, and we will also see how this affects the mechanical properties of different polymers. We will also look at how to measure this glass transition temperature. So, the way we will discuss it is by starting from a molten polymer. Once we decrease the temperature, how it solidifies. So, we will start with perfect crystallization. Perfect crystallization, bear in mind, it only occurs in metals, it does not happen in polymers, but we introduce these concepts so that this is something most of us are familiar with. We will use these concepts to explain how this crystallization happens in polymers. Okay. So, we are starting at this point, so where the temperatures are high and then we are cooling down. So, initially when we cool, you see that there is a linear slope downwards. So, why does this happen? So, what we are looking at is on the y axis is the volume, on the x axis is the temperature, which means as we are cooling the volume is decreasing. Why does this volume decrease? The answer can be explained by looking at what happens to these polymer chains at high temperature. At high temperature, because there is more and more thermal energy, these atoms or molecules or the chains, they are jiggling. So, which means they are taking more space than what is required, because probably this is the size of the atom, but because of this jiggling they are taking more space. But as you decrease the temperature, this amplitude of this jiggling decreases. Because it is decreasing, then it needs less and less space. So, this for a solid phase also we see the same thing, and that is called CTE, coefficient of thermal expansion. But now let us follow this. So, initially we said the volume is decreasing as the temperature decreases, but once it reaches this temperature Tm, what is Tm? Tm is the melting point temperature for metals. Then that is when there is a sudden change in the structure of the polymer structure. So, what happens is these atoms now start crystallizing. So, from here to here is the crystallization process, where these atoms which are currently very mobile as well as jiggling about their positions, they come in a very close and tight packing. So, for metals usually you might have heard about body center cubic lattice, FCC. So, these are the ways by which these atoms come together, and once crystalline they stay in that structure. So, when this happens, how does it affect the physical properties? So, we are saying that we say that the atoms are randomly arranged initially at high temperatures, but at melting point temperature they go from random to an ordered stage, which we are now calling it as crystallization. But during this crystallization, what we noticed from this figure is the volume decreases drastically or significantly by a large amount. So, the volume decreases sharply. We said viscosity is the resistance to flow, but when we have this ordered state of crystallinity, the flow is difficult, because once they are close by, there are these interatomic forces or the secondary forces which bind them together. So, it is hard to move them apart. That is the reason why the viscosity increases sharply, and this is by a very huge value just before and after the melting point temperature. So, this should give you an idea about how a perfect crystallization occurs, which is common in metals. But now let us see how this crystallization is different from the way polymers crystallize. So, this red line is the previous one we have seen, perfect crystallization, and this blue line is the one we will be discussing now, which is for imperfect crystallization. Okay. So, here too one thing we notice is when we are starting from high temperatures and we started to cool, initially we see this linear region where the volume decreases with temperature, because again as we have seen previously, this is like jiggling of atoms and these chains are now flowing again past each other, because currently it is at a very high temperature and these chains are mobile. We are talking about this region. Okay. But then when it reaches this melting point temperature, these polymers have a well defined melting point temperature, but how they are different from metals is there is a gradual decrease. Though the decrease is large, it is not like a vertical line the way we have seen with perfect crystallization. Here there is a gradual decrease, but this decrease is significant. So, the decreases rapidly, but not sharply. Now, let us see why this does not crystallize sharply. The reason is again related to the length of the polymer chains by what we propose as the average degree of polymerization. So, we have seen that a polymer, not all chains are of the equal length. There is a range, there are chains which are slightly smaller or slightly longer, shorter or longer. Because of this, the crystallization happens differently depending on length of the polymer chains. So, for these regions there is a range over which this reduction in the volume happens, and this is all because of the range of the molecular weights, like the way we have seen it previously, saying that the probability of a polymer chain with a particular dP is not fixed, but it varies in a distribution. But again since the volume is decreasing, which means these polymer chains are coming close to each other and they are aligning well, because it is crystallization means these polymer chains are coming together and bonding together with these secondary forces, it takes a very less shape and it takes the structure of crystalline or the crystal. But during this process the viscosity increases, because now since these chains are close to each other and then they have these secondary bonds between them, it is hard to move these chains apart, meaning it is hard to displace one chain from the neighboring chain. So, this is what happens in crystalline polymers. Now, let us look at what happens if there is no crystallization. So, we are talking about amorphous polymers where the crystallinity is hindered because of several reasons, like previously we have looked, it could be hindered because of atomicity, branching as well as cross links, and maybe also multiple subgroups. Now, for us to explain how the cooling happens, we are starting from this point at a high temperature, and this green line is what we are focusing on, which is the amorphous polymer. So, we need a concept to explain how it behaves, which is the free volume. What is free volume? It is the extra volume at melt temperatures due to wiggling of molecules. As previously mentioned, these molecular chains, because of at high temperatures they have this high thermal energy, because of these they are wiggling by large amounts. Since they are wiggling by large amounts or jiggling about a particular position, they occupy more space than what is required. This extra volume is what we are calling it as free volume. So, here is the free volume. This is the extra space which is required just because of this wiggling of these either the atoms or the polymer chains. But now to understand this process of how the liquid polymer ends up as a amorphous polymer, we will go in step by step process, we will go slowly. So, we are saying on cooling, so which means we are starting here and we are going downwards. What happens? Initially the liquid structure is retained. So, while it is a liquid, the molecular chain is free to move from one end of the polymer to the other end of the polymer, because it is not bonded with any other neighboring chains, it is free to flow past each other. But as it cools, we said the thermal energy is less, so this jiggling is less and less. So, since they are coming to the spaces are less, the difficult it flows, but there is a difficulty to flow. The analogy to think about is like a driving on the roads. So, if you are on a highway, because there is more space, the vehicles are usually going faster. But then when you come to a city road where there are more and more vehicles, then the speed is less and actually the difficulty to go faster is more and more. So, what is happening here is that free volume is decreasing as we decrease the temperature. But if we further decrease the temperature, we arrive at a point something like this, where the free volume is too small for molecules to move and rearrange. So, we are saying that initially the molecules are free to flow past each other, but that is all possible because of this extra free volume. But once this extra free volume is very much limited, it is almost like in a traffic jam, right. Once the vehicles are closer and closer, the chances of a traffic jam is high. The reason is because there is very little space between the vehicles. The same here, since there is very little space between the molecular chains, so there is a hindrance to the movement of these molecules. This point we are calling it as the glass transition temperature. So, the point at which we are saying that the free volume is negligible. The aspect, but how do we say it is negligible? It is negligible because now it is very difficult for this polymer chain to really move past each other, because there is not enough space. They are actually stuck in this traffic. But let us see what happens if we further cool down. If we further cool down below Tg, since now these molecular chains are very close to each other, then because of the proximity we have these van der Waals forces and the hydrogen bonds forming, which are the secondary bonds. Once these secondary bonds form, it is even hard for these molecules to move past each other, right. So, what we are saying is then they become because of these additional bondings, it becomes even more stiffer or stronger. So, to the left of this region we have the glass region. So, if you are still decreasing the temperature, what happens is now all these polymer chains are they can't move past each other, they are stuck in a particular configuration or position, but still there is some slight movement because of the thermal energy available even at these temperatures. But again as we further decrease the temperatures, these movements is less, and then again it there is a slight decrease in the volume, not as much as in the earlier position where the slope is high. Now though the slope is low, there is still slight decrease in the volume as we decrease the volume of temperature of these polymers. So, what happens above Tg means if we are looking at to the right end of this glass transition temperature, that is when all the secondary bonds are non-existent, because now we have free volume and they are not close to each other to form the secondary bonds. Since there is no secondary forms, the polymer becomes leathery, leathery meaning very soft. And then if the temperature is slightly more than this, then they behave rubbery. Rubbery meaning we have seen stretchy means soft polymers, natural rubber as well as tires, we categorize these as rubbery behavior. Okay. Here the take home is to understand what is this concept of free volume, saying that this is the additional volume the molecule is taking because of this additional thermal energy which is giving this jiggling or the wiggling of these polymer chains. And from this concept of free volume we were able to show what this glass transition temperature means, meaning that that is a temperature below which we have the glassy state, means the polymer is now a solid, but the structure is very random. How random is it? It is as random as what we have seen in a liquid state. So, above the glass transition temperature, that is when the polymer is leathery, meaning very soft, and if the temperatures are slightly beyond or far from the glass transition temperature, that is when the polymer is rubbery, meaning softer, flexible and all. Now, let us see how this glass transition temperature is important in choosing the kind of polymers for a particular application and how it affects the mechanical properties. So, in the previous slide we already mentioned about what happens below Tg and above Tg, saying that below Tg it is in the glassy state and above Tg is when most polymers behave as hard plastics. Okay. So, now let us look at an example of PMMA or polystyrene. PMMA is the plexiglass and polystyrene is commercial name of it is thermocol, which we use for packings. The glass transition temperature for this PMMA and polystyrene is about 100 degrees centigrade. So, in the order of 110, 120 and 100. So, what it means is the glass transition temperature is much above the room temperature. So, in this graph where do you think the PMMA is at room temperature? So, the room temperature will be somewhere here, right, because we said the Tg is already at 100 and the room temperature we know is around about 25 degrees centigrade. So, since this PMMA at room temperature is somewhere here, what we see is the glassy state, which means we see a brittle solid at room temperature. Now, let us look at another example of rubber, natural rubber used in the tires. This has a glass transition temperature of about minus 70 degrees. So, it is sub-zero. So, which means at room temperature where are we? At room temperature we are much beyond the glass transition temperature which is at minus 70 for rubber. So, let us say previously we said this is around P for PMMA and maybe we are somewhere here for rubber. So, I am just mentioning where the room temperature is with respect to the glass transition temperature. Since for rubber we have seen that we are above the glass transition temperature, we already know above glass transition temperature there are no secondary bonds. So, there is nothing binding to polymer chains together. The only reason why they are together if in case is because of a few polymer chains in case of elastomers. Elastomers, if you remember, we said it has very few polymer crosslinks. These crosslinks will help it to retain the shape, because once you stretch it is able to stretch because there are no secondary bonds and very few crosslinks, but again it will come back because of those very few crosslinks. And that is the reason why how we can now explain that the rubber is flexible, soft and elastic, meaning it will come back to the original shape. Here let me also explain what happens if you change the temperature of PMMA as well as rubber. So, we have seen how it behaves at room temperature, but the same PMMA or the plexiglass, if I keep heating, what happens? So, when it reaches Tg of around 100 degrees, that is when the glass transition happens, means it goes from the solid glassy state to the leathery state or the rubbery state. So, we are talking about temperatures beyond 100, which means maybe at 130, 140 or 150 degrees centigrade, that is where the PMMA behaves slightly soft and leathery and rubbery. The same thing with polymers, with rubbers. We said the rubber is flexible, but this is only we are talking about room temperature. What happens if I cool down the rubber? So, which means if we are using in sub-zero climates or weathers, until minus 70 degrees centigrade, it still has this rubbery state, because it is still beyond the glass transition temperature. But if we are going even further below the glass transition temperature, which means around minus 100 degrees centigrade or minus 120 degrees centigrade, that is when the rubber has now transformed into the glassy state where it now shows the solid or it becomes hard. The same rubber shows hard behavior when it is below the glass transition, which happens at temperatures in the order of minus 100 or minus 120 degrees centigrade. So, I think this is a very important point to remember, saying that we cannot say a particular material is whether it is glassy or it is leathery or hard. It all depends on the operating temperatures. If your operating temperatures are less than glass transition, then it is in a glassy state and it shows solid behavior. But if your temperatures are beyond the glass transition, that is when we have this soft polymer which is flexible. So, it is important to know this glass transition temperature, because it says for your operating conditions which polymer you should choose, whether you want your polymer at that temperature to behave as a solid high mechanical properties, or you want it to behave as a soft flexible material. Okay. Now, let us look at how do we measure these glass transition temperature. So, I will be showing you three ways how to measure the glass transition temperature, starting with differential scanning calorimeter. So, this is an old method to measure the glass transition temperature, where the heat given to the polymer is measured as we increase the temperature. So, because depending on whether it is in the glassy state or the amorphous state, it takes different amounts of heat, and that helps us to find what is the glass transition temperature. Second method is the thermal mechanical analysis, which is based on coefficient of thermal expansion measurements. So, meaning like you have a polymer and you keep heating it. While you heat it, you measure the dimensions of the polymer, so that you can comment or measure the thermal expansion in this polymer. So, from this information of the thermal expansion of the polymers with changes in the temperature, one can find what is the glass transition temperature, because the way the thermal expansions are there before and after the glass transitions are different. So, that transition we can pick and pinpoint what is the glass transition for a particular polymer. And the last and a more precise way to measure the glass transition temperature for a polymer is by this dynamic mechanical analysis, or in short DMA. Here what we are doing is, we are giving oscillatory strain, either tension strain or we are bending it or twisting it. This is oscillating, meaning you go into tension, compression or tension. So, but during this we are also measuring what is the loads or stresses in this behavior. From this, the way it behaves in glassy state is different from way it behaves above Tg. So, from that we should be able to find out what is the glass transition temperature. So, let us now summarize what we have discussed in this video. We were looking at what happens when we start with a polymer in a liquid state at high temperatures. We said at high temperatures it is in a amorphous state meaning which is the molecular chains are very randomly packed. But as we cool down, depending on whether there is perfect crystallization, then we see that there is a sudden change in the volume, and this happens at melting point temperature. This only happens for metals. But we said polymers, if they crystallize it, we get an imperfect crystallization, and for that imperfect crystallization we do have a well defined melting point temperature, but then this sudden decrease in the volume happens over a range of temperature. The reason for this range of temperature we said is because of the range of lengths we have in the polymers, or the range of degree of polymerization we have in a particular polymer. And lastly we said there are polymers which take an amorphous form like the one shown here in green, where when we decrease the temperature through this concept of free volume, we said this free volume decreases as we decrease the temperature, and then it reaches a point where this free volume is negligible, where the movement of the polymer chains is restricted, and then the secondary bonds form which give the solid behavior or good mechanical properties for an amorphous solid. Define this concept of glass transition temperature, which is very specific to polymers and which is very important to know for us to understand their mechanical behavior, as well as to for us to choose what is a good polymer for a particular operating temperature. And finally, we ended by looking at ways to measure this glass transition temperature. Thank you for your attention. We will meet again in the next week.